Okay, in this lecture video, we're just going to practice converting between mass, moles, and the total number of a chemical substance. And that total number might be total number of molecules, total number of atoms, whatever. But we're going to convert between moles, mass, and total number. So let's go back to the same example we were using before, which was 125 mg of water. And now we really want to know, how many moles is that? Right? So we know we're going to use molar mass because that's what allows us to convert between mass and moles. So we always start the calculation with the number we're trying to convert, in this case 125 mg of water. And we know molar mass is measured in grams, so it's always good to go to the base unit out of the metric system. So 1 gram of water is 1,000 mg. So now mgs have canceled out. Now we know the relationship between grams and moles because we know how to calculate the molar mass of water. So we know that there's 1 mole of water for every 18.02 grams of water that we have. And if we do that calculation, we find out that if we have 125 mgs of water, then we've weighed out on our balance 6.94 times 10 to the minus 3 moles worth of water molecules. Now, it could be that instead, how many total water molecules is that? So if instead I wanted to know total number of water molecules, I could do one more step in my calculation. So just starting from the beginning again, I could say I have 25 mgs of water. I know that 1 gram is 1,000 mgs. My mgs cancel out. I can keep going with that multiplication because I know that there's 1 mole of water is 18.02 grams. Now my grams have canceled out, leaving me with units of moles water. So that's where we stopped the last calculation we just did. But if I want the total number of water molecules, I now need to use Avogadro's number. Because for every 1 mole of water that we have, there are 6.022 times 10 to the 23rd water molecules. So if I do that, I come up with 4.18 times 10 to the 21 total water molecules. So I think you have to be really noticeable, too, of the exponent when you do this calculation. So when you're calculating the total number of something, and you're talking about atoms or molecules, something really tiny that you've weighed out on the balance, this number here should be big, right? Because they're so small that if you can actually see the mass on the balance, you've weighed out a whole bunch of them. If you get a negative exponent here, that's saying you have less than 1 molecule, and you know that's not true if you weighed it out on the balance. So it's a really good check to see if you're doing the math right, or if perhaps you've got one of your conversion factors upside down. So let's do another one. What if instead of looking at the total amount of water, we want to look at moles of oxygen? So how many moles of oxygen do we have in 125 mgs of water? Well, we could do this calculation again, and you can do these a lot of different ways, but we always start with the number that we're trying to convert. So 125 mgs of water, 1 gram of water is 1,000 mgs. So now our mgs have canceled out. And then you can only make relationships between an element within a molecule and the total molecule if you're in the counting the individual units or counting moles of units. You can't make these relationships while you have units of mass. And right now, we have units of grams. So we need to get out of that. So we're going to convert to moles. So we know 1 mole of water is 18.02 grams. Now our grams of water have canceled out with grams of water. Now we have units of moles of water, and we want to relate that to moles of oxygen, because we can make a mole ratio between an atom within a molecule and that particular molecule. So if we keep going with our calculation, we know that for every 1 mole of water that we have 1 mole of oxygen. And if you do that, you get the same number we got before. There's 6.94 times 10 to the minus 3 moles of oxygen when we have 125 mg of water. That's also the same number of moles of water because it is a 1-to-1 mole ratio. So if you have 125 mg of water, you end up with 6.94 times 10 to the minus 3 moles of water and 6.94 times 10 to the minus 3 moles of oxygen. If instead you wanted to know, well, how many grams of oxygen is that? With your moles of oxygen here, this point, and we've got the moles of oxygen, we could have instead multiplied by Avogadro's number. Cancel out with moles of O. Just keep going with the calculation. And you would do one more step. So if we keep going where we left off, which was the mole ratio of oxygen to water, if you do one more step and multiply by the mass of water, 6.0 grams of water, or grams of oxygen per 1 mole of oxygen, then your moles of oxygen cancels out, leaving you with units of grams of oxygen, which comes out to be 111 grams of oxygen. If instead you wanted to know total number of oxygen atoms, we could have, instead of doing this calculation up here, we could have done another calculation where instead, if we had done that, we would have done this step, knowing 6.022 times 10 to the 23rd atoms of O for every mole of oxygen atoms that we had, and then moles of O, leaving us with units of atoms of O. And if you did that calculation, you would get 4.18 times 10 to the 21 atoms, I can't fit it on my mini iPad, atoms of oxygen. So you should go through these calculations and see, for 125 mg of water, can you calculate the moles of oxygen, the grams of oxygen, and the atoms of oxygen? And then you should consider, how would that calculation have changed if instead of wanting to know moles of oxygen, you wanted to know about moles of hydrogen? So hopefully what you recognize is that based on the chemical formula of oxygen, that we know that there are 2 moles of hydrogen for every 1 mole of water that we have. So instead of having a 1 mole of oxygen for every 1 mole of water, you would instead be using this mole ratio, and then you would have been able to figure out moles of hydrogen. Given that the ratio is 2-to-1, if you were to do that calculation, you should come up with twice as many moles of hydrogen as there were moles of water. or twice the value of 6.94 times 10 to the minus 3 moles of water, because there are twice as many hydrogen atoms for every 1 mole of water that you have.